closed set. Before we continue this closed set, let me quickly bring your mind back to the closed ball. So we define closed ball as follows: BR bar equal to this. If you remember, this is the definition of our closed ball. So the only difference between the open ball is that there is a strictly less than sign here. But here there is a less than or equal to sign for closed ball. Now, before we define closed set, let us consider some definitions. Limit point of a set. So we'll define limit point as follows: let S be a metric space and let A be a subset of S. Point X inside A, this point X inside A is said to be a limit point of A, or we call it accumulation point of A, or we call it cluster point of A. If for every open ball this, the open ball intersection A minus this X will be non-empty. What this definition simply means is that if every open ball centered at X contains another point of A different from S, what that means is that for we to call S an open ball, S a limit point or accumulation point, X must first belong to A. Then that X, we call it a limit point. If there exists an open ball, that open ball we are talking about will contain S. That is centered on X. That is why we put it here. And also, the open ball that is containing S or centered on S will also contain another point of this A that is not X again. For instance, suppose S is 1, 2, 3. Suppose an open ball, suppose it's 2, 3, 4, something like this. What this is that here I will call 2 a limit point of A. Why? Because 2 is inside A and 2 contains in open ball here. Also, this open ball contains another point of A, which is this 3. There is 3 again inside it, so it contains it. So that is what we mean by limit point. So another definition: derived set. So if they say that derived set, we have talked about limit point. So the set of all the limit points of A. So if you have more than this, then that set is called a derived set. The set of all the limit points. For instance, if you look at this now, 2 is a limit point, 3 is also a limit point. So from that place, we can say that A, the derived set is this. So the set of all the limit points is called a derived set. And finally, the closure of a set. So let A be a subset of a metric space S. So the closure of A is the union of A and its derived set. So it's the union of A and its derived set. This is the derived set. And we denote closure of A by A bar. So that is to say A bar is equal to A union A complement. So this will now lead us to the definition of closed set. Closed set. So we define closed set as let S be a metric space. I can say that S command D as well. So let S be a metric space and let A be a subset of S. So we say that A is a closed set if it contains all its limit points. So that's the definition of a closed set. If a set contains all its limit points, then we say that the set is a closed set. So from this definition leads us to the following theorem. So we have the theorem here. A subset A of S, or let's say this set A, which is a subset of a metric space, is closed if and only if its complement is open. Although it's a theorem, we can also take it as definition. So this simply means that what this theorem is saying is that if A is closed, then A complement is open. Also, if A is open, then A complement is closed. So that is what the theorem is saying. So let us prove the theorem. So because of the if and only if that is there, we need to prove it in two ways. The first way, we will first assume that A is closed, then we prove that A complement is open. So now let's suppose that A is closed. So we have assumed that A is closed. So we want to show that A complement is open. So let us pick an element belong to A complement. So by the theory of set, this simply means that S does not belong to A. But remember that A is closed. So if S does not belong to A, that simply means that S is not a limit point of A. So then by definition of limit point that we just gave, we say that there exists an open ball centered on this X such that BRS intersection A, it will be empty. You know, we define a limit point that it will not be equal to empty. That BRS intersection this is not empty. But now S is not inside this A. Definitely we can't put this one there. So definitely it will be empty. Assuming it's a limit point now, then it will not be empty by definition. But now this thing shows that it is empty. So that the reason why we put empty there is because we have agreed there that it's not a limit point. Since we have said A is closed, then if S belongs to A, then S must be a limit point of A. But yes, it shows that S does not belong to A. So that is the reason why we are having equal to empty set here. And if this is equal to empty set, that means they don't have anything in common. So and this will simply means that BR of S is not a subset of A because they don't have anything in common. Definitely BR of S will be what? Will be a complement of will be a subset of this A complement. And by definition of open set, we know that if a set is open, then there exists an open ball which should belong to that set. So that this open ball belongs to this A complement. Therefore, A complement is open. So that completes the first proof. So secondly, now we now assume that A complement is open. We need to show that A is closed. That is it I've written out. We assume that A complement is open. Then we need to show that A is closed. So now let A complement be open. Also, here we have assumed, so I don't need to let. So A complement is already open because we have assumed it. So let us pick an X in A. If you pick an S in A, this means that S is we are assuming that we are letting S to be a limit point of A. So we now prove by contradiction. So suppose by contradiction X belongs to A complement. You know, we have said here said here that S is a limit point. So we now want to show by contradiction that S is not the limit point of this. So we want to show. So here we have assumed that S does not belong to A. Definitely S will belong to A complement. And if this happens by what we have said the other time, this is simply means that BR of S intersection A is empty. So this simply shows that S, this is A complement here because of this. So this implies that S is not a limit point of A. So this contradicts our assumption. So this contradicts It contradicts our assumption that S belongs to this. So in that case, S is a limit point of A. It's a limit point of A. Hence, A is closed. Now let's consider another theorem. Every closed ball in a metric space is a closed set. So proof. So let us consider a closed ball centered at S0. So let this be a closed ball. So what do we want to do? We want to prove that this closed ball is a closed set. So it is suffices to prove that this the complement of this ball is an open set. By definition, by the theorem we just proved that we say that a set is closed if its complement is open. So that is for us to show that this one is closed. So it will be better for us to show that the complement of this thing is open. And when we have this thing, this is what we are considering now. So let us pick an element in this place. X belong to this. So we have picked an element, as we have said, that S belong to this. So we know by the theory of set that S does not belong to ordinary this without a complement there. So we know that S does not belong to it. Now, if S does not belong to this, by definition of a closed ball, for closed ball, we normally say that y comma S naught is less than or equal to R. But since S does not belong to this, so this will simply means that this S comma S naught, here we are using y, here we are using x, this is our x naught, will not be less than or equal to R by definition of closed ball. And if this is not less than or equal to R, what do you think will happen? What will happen is that d of s comma s naught must be less than R. Must be greater than R. That will be the something, because it is not less than and it's not equal to. Definitely it must be greater than our R. Now from this place, if you bring this one in, we are going to have d of s comma s naught minus R is greater than 0. So we let our R1 be equal to d of s comma s naught. Let's let our R1 be equal to that minus R. Or if you make R the same formula, that is d of s comma s naught minus R1. So let's call this equation 1. And why are we even using this? Why are we saying that let our R1 be this? So let me explain it geometrically. Consider this closed ball. This closed ball here, centered at S0, and it has a radius R. Here we say that distance between, let's pick an x here, as we said in this case, that distance between S and S0 is greater than our R. So definitely S0 will be outside. It will be outside. So this is S, this is S, and this is S0. So this place is our R1. So you will all agree with me that this small R here will be equal to the distance between S and S0, the whole of this, minus this R1. Or we just quickly write it as S comma S0 minus R1, which is the same thing as this. So that is how we got this. That is why we are letting our R1 to be done. So let us keep this equation 1. So we need to consider, since we want to show that it's an open ball, so we need to consider another ball. So let us consider an open ball BR1X. So the open ball we want to consider now is that we want to consider one ball here. The ball will be centered at this S, and it will have this thing as our radius. So the question is that we want to show that BR1 comma of S is a subset of BR of S naught. So that is what we want to show. And how do we show this? The simplest way to show it is that we are going to pick an element inside this BR1 S. And if you show that that same element is inside this BRS naught, then we have shown that this is a subset of this. So in this case, it should be a subset of this complement, because it is the open ball. It is this that we are showing. We want to show that this complement is open. So let us represent y by this. Let y be equal to BR1x. If by definition of open ball, we know that this will be d of y comma x is less than r. Now let's keep this as equation 2. So by a triangular inequality, we have that d of s comma s naught will be less than or equal to d of s comma y plus d of y comma s naught. So this implies that d of s comma s naught will be strictly less than, this is strictly less, d of y and s, d of s and y, they are the same thing since d is a metric. So this is strictly less than r plus d of y comma s naught. From this place, you would all agree with me that d of y comma s naught is greater than r minus d of s comma s naught if you make this one the same formula. Now by equation 1, we will see that this is r1. We are dealing with r1 here. It's r1. This is r1. This is r1. Because we are talking about r1, not r. So that is a mistake. You can correct it. By our equation 1, we say that r is d of s comma s naught minus r1. So this simply means that d of y comma s naught is greater than our r. And whenever we have this thing, it will simply show that this thing, it simply shows that d of y comma s naught is not less than or equal to r, just like what we did the other time. That is, d of y comma s naught does not belong to the closed ball of this. Y. This means y does not belong to that, and this simply means that y belongs to BR s naught, then complement. So we have now shown that we pick y in this ball, and we show that y belongs to this thing. So this simply shows that this is open. So it's an open set. So and consequently, BRS naught is closed, and that completes our proof. So another definition we will consider is dense set. Let S be a metric space and let A be a subset of S. We say that A is dense in X if A bar is equal to A, and we have known what A bar means. A bar means A union A this, and A union A this. This simply means closure of A. So if the set is equal to its closure, then we say that the set is dense. It's dense in X. So for instance, R, Q complement are not dense. R means real number, Q complement means a rational number. This Q means rational number. This one is dense. So this one is dense so this is dense in R. This will lead us to another definition. Separable space. We say that a space S is said to be separable if it contains a countable dense subset. So remember we have said the other time that a rational number is dense in R. So in that case, we can say that R is separable. Why is it separable? Because it contains this rational number. We said if it contains a countable, that is finite. Countable means finite. That is, if it contains countable dense subset. So this, it has only, remember, real number is union of rational and irrational. So it has only countable, it has this. So which is countable? It has just one dense subset. So in that case, our real number is separable. So we'll meet in another class for another interesting topic.